Hello everyone, how's it going? Hello, we got any new faces, any old ones? Welcome to our current in circuit web class. The two parts are pretty much the same. In each part, we'll look at a new thing, we'll learn a new thing, and then we'll do a couple of questions on it. So yeah, how's everyone doing? Can everyone hear me okay? The house. That's what I did today. I tidied my room and I cleaned my house. It was incredibly boring, so I'm glad to be doing something else. Has anyone done anything more exciting than cleaning their room? Sorry about this. I think we're having a couple of technical problems. Just trying to fix that before we get going. Yeah. No, apologies for this. Okay, can people hear me now? How we? Can anyone hear me? No, not hearing much back, which doesn't make me too confident. Let's see. All right. Okay. Well, I guess what we'll try and if you miss anything, if I should have gone through something, but the audio cut out and you didn't hear it, then just let me know, and I'll go back through it again. Okay. Hello. Sorry about this. Hey. Can't hear anything. My screen is frozen. My picture's lagging. Okay, I'm gonna try and go ahead with the class. Sorry about how the lag seems to be. Like I said, if you miss anything, just let me know. I'll try and go back over it. We'll see what we get to. All right. Okay. Since we seem to be set up, let's get the show on the road. Okay. So. One second. Okay, so hopefully you can very happy looking piece of electricity, and we'll see where we get to. Okay, so today is about current circuits. Just a bit about Snap Revise and a bit about me before we get going. So my name's Matt, doing this with that. I'm in tutoring A-level physics for at least 4 years now. I think after 4 years, you stop counting and just say kind of a few years. Anyway, so this is all very fresh off my head now. So we're essentially doing a trial web class session today, a trial tutoring session. This is something that between me and James, another person in physics at Snap Revise, we do about 4 sessions a week at the moment, like this on Revise website. So you can get a two from that by entering the code TUNE to Snap Revise. So I hope to see you on with today. Today is current in circuits. And our objectives are to understand how to draw some circuit diagrams and identify components. So that's essentially just going to be listing some components, just reminding us of some things. And then the key thing that we're going to be doing today is Kirchhoff's laws, which is a kind of intimidating name for actually a couple of quite simple rules on how current and energy are kind of used up as you go around a circuit. Okay, so we're going to start by doing a kind of refresher on the things that we're going to need to know today. So I want to start by that is a current, and a current is just something to do with moving charge around. So what are the units for charge? Usually give charge the symbol and for it, there are two kind of fundamental. Hopefully we're back. Coulombs, absolutely right. Yeah, sorry about the bad lag, everyone. Yeah, so you're absolutely right. Charges in coulombs. We sometimes say +1 if we're in units of the charge of the electron. Can anyone tell me either by an equation electrical energy. I am still lagging. Okay. How are we doing now? Am I back? Let's see. Yeah, absolutely. Capacitors are used to store electrical energy. That is precisely their use, in fact, actually, yeah. Okay, so some weird things are happening here, aren't they? Yeah, we're lagging pretty bad, aren't we? Okay. Okay, 1 second. Let me just fix things up quickly. Okay, right. Let's see where we can get to. Sorry about this. Okay, so what is so as an equation that's often written as round when we're thinking about normal circuits, our okay, so the third thing that we need to introduce, we're sorry about the cutting out equations, but it would be nice to get a word. Because the equations are actually basically the same. The equation for EMF is epsilon is equal to E over Q. And hello, my sound is lagging. Probably you can't properly hear me. Damn. You can't really hear me now. Okay, hello everyone. The rate of flow of charge. Okay, can people hear me at the moment? How are we doing? No and yeah. Okay. Right. I'm gonna keep trying to go through it for now. Do just stop me. Okay. Let's see where we get to. You can hear me clearly. Awesome. Okay, great. Let's see where we get to. So EMF is defined as the energy per charge moves through a component. Moves through a component. So EMF is the kind of thing that you get from someone else, for example. As soon as I share. Okay, it's something to do with the sharing. That's interesting. Yeah. Yeah. Sorry, 1 second. Hello? Yeah. Okay. I'm going to keep pressing on for now. I think if it happens one more time, we'll have to think about restarting or something. Okay. You can hear me now. Yeah. Now I've just shared my screen, and we'll see what effect that has. Okay. So we're still on the refresher slide. I was just saying about how EMF is about picking up energy as you go through components, usually things like cells, for example. The second kind of thing we're interested in is the kind of components in which we might lose energy as a charge is the energy per charge lost as charge passes through a component. Okay, it is very fuzzy. Yeah, do just let me know if you need me to repeat anything. Okay, and so again, this is given by V. So we use the symbol V for potential difference rather than epsilon for EMF. But again, it's given by the same formula. It's just energy per. So now we're ready to go on to the main part of the session. Let's see where we get to. Okay, So just before we start on the main material, here's the spec points for the various exam boards. So if you're on AQA, OCR, or at Excel, you'll be able to see the spec points for the stuff that we're going through. Okay, there's at Excel. And now let's get going with the main section. So the first part, all we need to do is just name a load of circuit components. So I'm going to label these component 1, 2, 3, 4, 5, 6, 7, and 8. And if people could type in the chat what they think each of these components are, see if you can race me to some of them while I get into it. So I'll start us off. The first one is a switch. So there's a switch. So a switch is something you can do. Absolutely right. Number one is a switch. Good. 2 is a diode. Good. Okay. And so at this point, while you guys are thinking about that, I'm going to just talk about this picture on the left-hand side. So on the left-hand side, we have the basic components that usually come up in any circuit diagram. We have, first of all, a cell over here. And a cell, as we were mentioning before, is a thing that has an EMF. It's a thing which gives charge or gives current some extra energy as it passes through. Good, nice. Okay, I'm liking these answers. Sweet. So this is an LED. Good. Thermistor. Good. Okay. So an EMF or a cell is a thing which and we draw an arrow to show the direction it's going around the circuit. There are some basic components here, which I'll get us to name in a second. So going back to here for now, absolutely right. This is a lamp or a light bulb. Good. This is a variable resistor. Good. Number 7 is an LDR. Absolutely right. A light-dependent resistor. So we'll explain what that means in a second. Good. And the last one here is the purpose of storing electrical energy. Okay, so let's talk about what all these components do. So the basic component, the cell, pushes current around a circuit. If we want to know how much current we have in a circuit, we can use what's called an ammeter. So that's this box here. This component here is an ammeter. An ammeter is used to measure the current. So for example, it might measure something like 5 amps, which means the current is 5 amps. Okay, next we have a voltmeter. And the purpose of a voltmeter is to measure potential difference, or alternatively, its purpose. Okay, so it's put across a circuit to compare. It's put across a component, sorry, to compare either side of the component to see what the difference in potential is. I'm sorry about the lagging. Lag isn't too bad. Okay. Well, like I said, just let me know if you need me to go back over anything. Good. Okay. So the final component here, super important one, is a resistor. And resistors lost. They are resistors. They don't want to let charge through. And so when charge tries to get through them, it has to spend some energy, has to spend some potential. Good. Okay. So then we can move on to these components. A switch is something which breaks a circuit and stops the current from getting round, routing it off into kind of thin air instead. Good. Okay. Is the lag okay? Okay. Good. So in our web class next week, we're actually going to go through the kind of the purposes of these components in a bit more detail. For now, you just need to be able to identify them. That's all, because they might appear in circuits. Okay, so the main thing I want to focus on in this part of the session is Kirchhoff's first law. Not as bad as it was. Okay, cool. So this is a super important rule. So I will definitely repeat this if people don't catch it. So it's called Kirchhoff's current law, and it's about what happens when a circuit splits into two or more parts. Now, Kirchhoff's current law follows from a very basic principle called the conservation of charge. And when applied to a circuit, that principle just says that the total charge present in a circuit must be constant. The charge carrier is moving around. It essentially has some electrons that are moving around in various places. Now, the electrons can't leave the circuit. They're all moving around in a circuit, but they can't leave. And so what that means is that the charge entirely inside the extension of this is to think about what happens when a circuit splits into two. For example, when we get to this point here. So we've kind of zoomed in on this and written it over here. So here's the idea. Let's imagine I have some charge flowing around the circuit. I have some charge Q. And let's say that, well, whatever charge enters this splitting between the circuits here must end up in either the top wire, wire 1, or the bottom wire, wire 2. So there will be some charge Q1 that ends up in the top wire, some charge Q2 that ends up in the bottom wire. And overall, we know that the charge that went in, Q, should be equal to the charge that came out of wire 1 plus the charge that came out of wire 2. Now, extension of this is to divide everything by time. So if you divide everything by time, you see that the current coming in should be equal to the current coming out of wire 1. This is a really important rule, which is going to come up a lot when you analyze circuits. Okay, so Kirchhoff's first law states that the total current, this is what you really need to remember, the total current which flows into a point, which flows into flows out of that point. Flows. Fix the important rule. The current going in is equal to the sum of the currents going out. Still lagging a bit. Okay, well, this is a good opportunity for people to ask questions. Okay, so how we... Anytime I share my screen or type, it goes a bit south. It's strange. Yeah, as in draw on the screen. Yeah, makes sense. Repeat what Kirchhoff's law is. Yeah, absolutely. So here we go. Kirchhoff's law states that the total current which flows into a point is equal to the total current which flows out of that point. So by a point, I mean a place where where a circuit splits into two. So the classic example would be this place here. We've got some current flowing in I. Kirchhoff's law says that the current flowing out in one direction plus the current flowing out in this direction is equal to the current that flowed in. In other words, I is equal to I1 plus I2. So that's the important rule. Sound good? No worries. Okay. So, yeah, how are we feeling? Okay, maybe let's try and have a go at some questions, see where we get to. Okay, so I have a feeling these graphs might look a little bit grainy for you. So I'll try and, no, it's not usually lagging like this. Not quite sure what's happening today. Yeah. Okay. 1 second, because my picture has disappeared, hasn't it? Okay, so I know if you can see the question. So it's question 1, and it says 2 6-volt torches produce similar light intensities. The light source of one is a single filament lamp, and the other is a combination of 4 light-emitting diodes, or LEDs. So figure 1.1 shows the IV characteristics of the filament lamp and one LED. Okay, so we have 2 components, a filament lamp and a light-emitting diode. And these IV characteristics are just fancy words for a graph of current against potential difference. So they're taking some component, we won't say what it is just some random component, and they're graphing the current that goes through it, which is I, against the potential difference across it. Represent, and now we're going to be asked some questions. First of all, we're asked to define potential difference. So that's great because that's something we've covered. Potential difference is, 1 second. Okay. Potential difference is the work done or energy lost is fine. The work done per unit charge as charge moves through a component. Charge, it's energy transferred per charge. Good, so part 2 asks us to use figure 1.1 to determine the current through each LED. So we have to, we need to go back to looking at these graphs. We need to try and harvest some information from the code we have. The LEDs and the LED torch are connected in pairs across a 6-volt battery. The potential difference across each of the 4 LEDs is 3 volts. Okay, so we know the potential difference, V, is equal to 3 volts. Let's see if that'll help us when we look back at these graphs. Well, what did they want? They wanted to know the current through an LED. Well, here we have a graph that shows the current through any LED when we know the potential difference. They said the potential difference was 3. And so as a result, the current must be 30. And what are the units? The units, okay. So the current must be equal to 30 milliamps. Always good to give the units at the end. Okay, lastly, we're asked to sketch a circuit diagram showing how the battery, the 4 LEDs, and the switch are connected in the torch. Now, this is kind of a funny one because we have to read the question quite carefully. So, okay, the LEDs and the LED torch, because we have to draw a circuit diagram just using this sentence here. Okay, they're connected in pairs across a 6-volt battery. Okay, so first of all, we know we can draw ourselves a 6-volt battery. So there's that. Thanks. So there's a 6-volt battery. Pairs. Okay, so now we need to remind ourselves of what the circuit symbol for an LED was. So an LED was given by this symbol. You see how sometimes you don't need to know anything about what these components are or what they do. You just need to be able to draw the circuit symbols. So there's our LED. Good. So that's the symbol we're going to need. And then we'll take a look at what they're asking for again. So they're connected. Here we go. There's LED 1, and they're in pairs. So let's draw another LED, LED 2. And they say each of these pairs is across the 6-volt battery. Great. Okay, so here's what we have. There's the first pair, and here the circuit splits into a second pair, which we'll draw here. Good, and that's all they're looking for. Okay, so next question. Good. So for this question, we're given another IV characteristic, which is again just a fancy word for a graph of current against potential difference. Okay, for 2 electrical components, a resistor, line R, and a thermistor, line T. Okay, so I want to open this one to you guys. State Ohm's law, because we haven't talked about this yet. So can anyone state Ohm's law, and can anyone explain from the graph why component R satisfies Ohm's law? So you can go for either, you don't have to give both. Ohm's law is, or why the graph for R shows Ohm's law. Each of those would be really, really useful. So what's Ohm's law? It's a straight line and it goes through the origin. Nice, yeah. For an ohmic current conductor at constant temperature, V over I is constant. Good, so I've seen 2. Nice. So I've seen things about what Ohm's law is, and we just need to relate the two. So first of all, we'll say what Ohm's law says. So Ohm's law says that at constant temperature, current difference to voltage V. So how can we see this through the graph? The good news is they're not asking us about the curved line, so we can totally ignore that one. Exactly, physical conditions kept constant, really nice. Yeah, these are really good answers. Okay. And it shows Ohm's law precisely because a straight line graph is a direct proportionality. Okay. Since the line R is straight, good. Really nice stuff. What about the curved line? The curved line they're going to ask us about soon. But so far, we don't need to answer that because they just ask us to explain why component R obeys Ohm's law. Okay, good. So next question. Resistor and the thermistor can be connected to a variable voltage supply of negligible internal resistance in two ways. Here we go. The supply is varied in each circuit until the current drawn from it is 0.6 amps. Great. Okay, use data from figure 2.2. That's the previous graph, so we'll go back to that, to explain why the EMF E of the supply is 3 volts in this figure. Okay, so we need to explain why the EMF in this picture is 3 volts. Why is this thing here 3 volts? Well, before we even go back to the graph, let's just check what else that 3 volt tells us. What's the potential drop across our resistor here? And what's the potential drop across our thermistor? Does anyone know? So each of these is going to be 3 volts because of Kirchhoff's voltage law, which we're actually going to come to in the next part. So they're asking us to explain why it must be the case that when this current is 0.6 amps, each of these voltages must be 3 volts. So let's take a look back at the graphs. So they're interested in having 0.6 amps going through the two components. Now, how can I have, if I go back to this question here, remember that if I have 0.6 amps going into a node, Kirchhoff's current law says that these two currents, say the current through R and the current through the thermistor, must add up to 0.6 amps. So IR plus IT is equal to 0.6 amps. So if we look back at this graph, let's see what happens when the voltage across each component is 3 volts. Well, indeed, when the voltage across each component is 3 volts, the current through T, IT, would be equal to 0.2 amps, and the current through the resistor would be 0.4 amps. And that is exactly then when the current would add up to give 0.6 amps. So they've told us that the current is 0.6 amps, and they ask us to explain why the EMF is 3 volts. So what we can say is the following. We can say that for the EMF to be 3 volts, the potential difference across each component must be 3 volts. The graph shows hello. Okay. So let's get us back to where we were. So the graph shows that this occurs exactly when IT, the current for the thermistor, is equal to 0.2 and IR equals 0.4, which law is it disappeared. Okay, am I back? Okay, so we've explained why it is that a current at 0.6 amps leads to having a free voltage drop across each of these components. Okay, so let's move on to the next part. I'm just going to reshare my screen again. Okay. Good. Okay, so the second part is about energy in circuits, and I'll try and get through as much of this as I can. Of course, because of all the lagging and stuff, we've fallen a bit behind, so we'll see where we get to. Okay, I'm going to talk about now. And the second law is not about charge, it's about energy. So it follows from the principle of conservation of energy, so we'll start there. So the total energy given to charge carriers as they go around the circuit must equal the energy that they lose as they go around the circuit. Must equal the total energy that they lose as they go around a circuit pool. So let's say we have this circuit here. We know that as we go around this circuit in this loop, that all the energy that we pick up should be the same as all the energy that we drop. Now, that should be true for any piece of charge that goes around here. And in particular, that means that the energy per charge that we pick up as we go around this circuit should be the same as the energy per charge that we lose as we go around the circuit. In other words, the EMFs that we pick up through this cell and through this cell must be equal to the potential differences that we drop across this resistor and this resistor. So a basic version of Kirchhoff's law, which we haven't stated in full yet, a basic principle should be that E1 plus E2 should be equal to V1 plus V2. Now we can do this for any loop in a circuit, so this might be the slightly more surprising thing. So in a more complicated circuit, like this one on the right-hand side, we could use this kind of equation for this loop. Let's call this loop 1 or loop A. I think that's better. We could do it for this loop, loop B, or even more mad, we could do it for this loop. So in either case, you can say, okay, let's say we have some EMF here, some voltage V1 here, some voltage V2 here. The EMF that we pick up in loop A should be the same as the potential difference we lose in loop A. So E should be equal to V1. Doing the same thing for loop C tells us that E should be equal to V2. The general principle, and now we'll state it with words. Kirchhoff's second law says in any closed loop, of a circuit equals EMFs from all the cells, and they should be equal to all of the drops across all of the resistors, for example. Good. Okay, so let's look at an example where we get to apply this law, because I think this is the best way to get used to it. So I want you guys to help me get through this example. It's quite an interesting one. It's also looks initially quite complicated, so I think it's a really nice example. Okay, so we're first of all going to try and figure out this potential difference here across this light bulb. So I'm going to use this loop here. This loop, I'm going to call it loop 1. The voltages in the circuit. What's the EMF that I pick up? Well, the EMF I pick up is through this cell here. And I pick up 24 volts. So that's the EMF that I gained, 24 volts. Now, what did I drop in this loop? Well, I dropped V2, which is an undisclosed. And I also dropped 12 volts through this light bulb here. So plus 12. So immediately I have an equation that lets me figure out what V2 is. I can rearrange this to show that V2 is equal to 12 itself. So we can fill that in now. 12. Okay. So let's say I want to try and figure out V3. I'm going to do that. So here's V3 here. I'm going to do that by using this large loop. So here's the large loop. Let's call this loop 2. So what potentials what EMFs do I gain as I go around this? There's a 24 and what else? In the meantime, while I'm writing down that bit, can anyone tell me there are 2 components I go through around this big loop and around the entire circuit where I would actually lose potential. And so I'd like to know what the total potential dropped in this loop is. Okay, so the other EMF that I gain is this V3 here. Okay, so what potentials did I drop? Nice, 21 volts. How come? Well, we already showed V2 was 12. And then across this light bulb, or this lamp, I dropped 9 volts. So altogether, I have 12 plus 9, which is equal to 21. Now, something quite interesting is going to happen here. This means that V3 is actually equal to 21 minus 24, which is minus 3. So I'm going to go on to using the third, trying to figure out the third missing thing in this circuit, which is this current here. In the meantime, can anyone suggest what this means for this cell here, if it has a voltage of minus 3? It's quite an interesting question. It's quite good for your understanding to think about that. It actually means that something is drawn slightly wrong in the top of the circuit. Yeah, so it means it's a cell that has an EMF of 3 volts, but it must be pointing the other way. So really, what this top thing is like a cell which actually points the other way whilst having an EMF of 3 volts. That's what it means to have a cell pointing this way with an EMF of minus 3. It's like it was put the wrong way around in the circuit. Exactly. Yeah, exactly. It means it's actually pushing in the other direction. Perfect. Really nice. Okay, so part 3. So for part 3, what do I want to find out? I want to try and figure out some of these currents. Let's try and figure out this current here, I2. How can I figure out current I2? It's going to be using Kirchhoff's current law. Well, you might be able to see that the current in the top loop must be everywhere 6 amps, because the current is the same everywhere in a series circuit. The current is 6 here, so the current must also be 6 here. The current is 9 here. And we have these arrows telling us that the current is coming out of the node here and here. So the current must be going in here. And so this current must be equal to the sum of the currents going out. So I2 must be equal to 9 plus 6, which is equal to 15 amps. Good. Awesome. Okay, so how is everyone feeling about this? I'm really sorry about the lags, and do let me know if you have any questions. I'm glad it's helpful. So how are we feeling? Are we feeling good? Are we feeling bad? Straightforward. We've got a straight forward and a straight mouth. Cool. Okay. All right, let's try and have a go at some questions quick with our remaining time. So let me just see where we're at. And we're dabbing. Sweet. Okay. So I'm not going to get the chance to go through all of this just because of the lagging at the start. We've ever so slightly run out of time. And after this, I'm off to do some more sessions on Snap Revise's website, which if you use the code, you can come to the future ones. So I'll just quickly have a chat about a couple of these bits and then we'll finish up there. So, okay, figure 4 shows two resistors, R1 and R2, connected in series with a battery of EMF 12 volts. Okay, the reading on the voltmeter is 8 volts. Let's write that here. Oh, my apologies. 8 volts. And the resistance R2 is 60 ohms. Okay, there we go. 7AI, we're asked to calculate the current in the circuit. So I'm just going to very briefly take us through these questions. So I won't, usually I would ask you guys to do them along with me, but because we're a bit short for time, I'll just run in. So, okay, we want to calculate the current in the circuit. Well, we know this resistance. We know we have 8 volts here. We know we have 12 volts here. Altogether, the EMF that we gain must be the same as the potential difference we drop. So the potential difference across R2, that's V2, should be plus V1 should be equal to 12, which is equal to 12 minus 8, which is equal to 4. Then the current through this resistor, which will be the current anywhere in the circuit, is equal to V2 over R2. In other words, it's equal to 4, the voltage across the resistor divided by the resistance of the resistor, and 4 over 60, that should be equal to around 0.067 amps. Now, I'm really sorry. I'm going to have to stop going through the actual questions there. I think you all have. The rest of the notes. If you, I think they were posted in the chat, so you can have a go at the questions. And actually, if you take our trial, you'll be able to come to our sessions, I believe, for a week or two. And you could even ask about some of these questions in our drop-in session, which I'm just going to explain now. So I'm just going to take us to the end. Sorry that we didn't quite go through everything. And while I'm doing this, let me know if you have any questions. So there's some web classes coming up, chemistry, maths, and we also have GCSE ones now as well. Great. So I just want to let you know about what we're doing on Snap Revise. We're basically doing these, usually with much less lag than we had today, so apologies for that. We're currently doing 4+ classes a week, so classes like this. Well, 2 of them are like this, and 2 of them are actually a bit different to this. So 2 of them are drop-in sessions where you can come to me with any questions you've got, any stuff you've been struggling with, you know, past papers you've been trying to go through and you don't understand the answers, and you can ask me about those, and we can go through them together as a group. So I'm actually gonna just give you a bit of a show of how that all works now. So just bear with me 1 second while I sort that out. Okay. So, great. So, welcome to Snap Revise, and you have the opportunity for a free. Trial. So do please join us on here. It'd be really nice to see you. It'd be really nice to have lots of people there so we can discuss various questions and so on. I just want to give you an idea of what I'm doing on Snap Revise at the moment. Basically, it's this, like I said, but with less lag and more sessions. So I'm doing physics, so I'm going to take us into physics. And here's the idea. Essentially, we're trying to replace tutoring in a way. So rather than £50 per hour for kind of a tutor, We're now instead saying, well, what if we did 4 lessons a week? So that would be, around 16 a month, and just charge 50 for the month. So we're trying to make tutoring a more cost-efficient thing that more people can have access to. And so I'm really enjoying doing it. And I think this might be a snapshot. Oh, this is a snapshot from one of mine. As you can see, it's not too grainy that time. And there's a huge schedule here for all the sessions that are happening. So you can actually see that we just now, a minute ago, I should have started astronomical distances and redshift. So I'm going to go and do that now. And after that, I'll be doing a drop-in session where people can come in and just ask questions, anything they've been struggling with, and we go through them and I answer them with you together. So please come and join us. It would be really nice to see some of you there. And you could even ask questions about the stuff that we didn't get a chance to go through today. So yeah, it would be absolutely lovely to see you all. I'll just leave you with the code, which is here. And yeah, hopefully see you all there. And thank you so much for coming. And thank you so much for bearing with all the lag problems. Cheers. Cheers for coming. Okay, so I hope you've all got the Tutor Me code down and it's in the chat. So I'm going to go off and teach some more classes and see you all there at some point. All right, bye everyone. Thanks so much for coming.